we're told that AC and EG are parallel. And so one thing that can be helpful is extending those lines out, and also these two, because now we start seeing it like more like the figure that is in your notes, the definition of all these different angles. It kind of helps. So for example, I'm not going to mark that these are parallel, but 68 and 4 have a relationship now. It's easier to see, hopefully, which is what kind of angles?
Same side interior.
Same side interior, so 68 plus 4, and I'm going to say measure of angle 4 equals 180. Those are same side interior. I'm going to do SSIA for all of those. SSIA, same side interior angles. Okay, so obviously we just subtract 68, and then what does that give you? Now, one thing, remember I told you I don't want you looking like you could never put a protractor on this angle and measure it. That's not drawn to scale. However, does 4 look like it should be obtuse, like a number greater than 90?
Yeah.
Yeah, and so if you solve this and you got like 23, something's wrong, because it shouldn't be a acute angle. So now we have 4, and let's see, I'll use this color, I think, and this is going to be 112 degrees. Okay, you don't have any particular order, and one thing that's true, you never have to go like 1, 2, 3, 4. Don't feel like you need to do that. But where could we go next?
1.
Yeah, so like 68 and 5 are what kind of angles? Well, right now we would be looking at these as the inside of the box. So 5 is outside and 68 is inside. Anytime you have that combination, we're probably talking about corresponding. So this is also 68, and it is corresponding angles. Alright, what about 68 to 2? Do you see a relationship there? It's also corresponding, yeah, so 68 degrees, corresponding just like 5 was, but on a different set of parallel lines. So that's an important thing too, is like which set of lines are you using to do this. Alright, and then how about 1? And for now I don't care which angle you use, but what can you do with 1? Do you see how it is a linear pair with 5? That's one way. Same side interior with 68. Can we use alternate? We can, but it's this angle. So the alternate interior angle with 1 is that angle. Does everybody see that? So you could, if you had that angle, you could use it to get 1. But we know it's 112.
Why is it that?
Why is it this one?
Yeah.
Like that whole thing?
Yeah, because doesn't that have?
Well, okay. Let's draw the system that we're looking at. So our parallel lines are these two, and then this line. So 1 is here. That makes this one its alternate interior.
Oh, okay.
Yeah. Yeah, and that's another strategy, is to like pull the pieces out that you're looking at, because it does get busy, and this is not like this is an exception. It's definitely going to be that way. With that said, though, do you see how 112 can be copied here because of alternate interior? And then we can get this angle. It doesn't have a name, but I labeled it angle 9. By what?
Vertical.
That's vertical. It's like opposite sides of the x, right? So that's 112 as well. I did just make up some of these, and so I was hoping that you would notice.
Can I do lunch attentions real
Yep.
quick? Perfect. Thank you. Zoe, Jesse, and Corbin. You guys have lunch attention in the small gym after this class.
Do you know how many days I have left?
It doesn't tell me anything. I just gave name and the ring number.
Okay.
That's Zoe. She
Okay.
checked in just now, but she's not in here.
Okay.
So if you see her, okay.
All right. Sounds good.
Thank you.
Thank you.
So anyway, I was saying I just put numbers in here, and I wanted you to decide if you could figure out the angle. Like 6. What is 6? Aha, that's what I was trying to tempt you to say.
Not drawing a scale.
Do we know if it's 90? Could it be 89? Or 91 or something? It should be 90, but we can't say for sure unless we can prove it. Is there any way to do that? Same with 7. Do we have any known special angle relationships that we can prove it with? Probably not. How about 8? Can we get 8? You guys remember isosceles triangle that we talked about yesterday? If we knew J to A and C to A are congruent, those two lengths, then these two angles would be congruent, and then we could subtract and divide, right? So 112 divided by 2, if these two angles are congruent. So, how about angle F? Can we get it? We can get angle F, so that would be good. What is angle F?
68.
It's 68. So angle 3 is 68 by what? That's vertical. It actually is vertical in this case. I think that's probably that's as much resolution as we're gonna get. So 6, 7, and 8. I'm pretty sure we can't get. We could maybe use this little triangle right here, but we need to know that angle, and that's not formed by any parallel lines. So that's about all. Did anybody get fooled by 6, 7? No, you don't have to say. Okay. All right. Well, let's check that homework. This is my work, so if you can't read it or need to see it somehow else, let me know. But these two are what kind of angles? Hold on. You're right, but good job. What were they? Okay. So I have like this side of the room saying it, this side of the room also participate. Alternate exterior angles are, they're congruent, so set them equal. And you can see that I set them equal there. And then because there's the bx term, we're moving this over and setting equal to 0. Don't forget to factor that GCF out, and then just do the star on the inside, which is way smaller than what you had of 19 something. When you do star, you're looking for factors of -30 that add up to 1. And we get -2 and 5/3 for the answer. Now, do both of those work? If I take that x and plug it back into the figure, do they both work? Now, this one would be negative if I plugged in -2, right? So we're not going to have a negative angle. On the test, I don't know if anybody's noticed this on yours, but which answer? I can't remember what answer it was. I think it was like number 2 or 3 had a negative answer that actually worked. And some of you are just like, nope, doesn't work because it's negative. But remember, you have to check that. Don't just say it, because that actually, both of the answers worked on that one, on your test. If you want to look at that, please come in and do that. I hate this. I can't see the scroll bar. There it is. Okay, did you guys notice that every one of these was number 4, I think? Yeah. Alright. Having trouble moving this around. Why? There we go. Alright. So next one, measure of angle 1 is something I can't read. What does it say? Can you guys read it to me? 3x plus 16, is it squared? Oh, it's degrees, right? So this one's just linear, and these are what kind? Same side interior, so they just add to 180. So just set them equal to 180. Add them and set them equal to 180 and solve, get 38. The next number 4, those are corresponding. I wrote that on there. Does -4 work in this one? Well, plug it into the linear term first, and no, it doesn't. It'll make that negative. So you only have x equals 1 as the solution. And then this next one, what kind of angles are those? Right, and what kind of angles are 1 and 2? Yeah, I'm seeing some funny faces because do they actually have a relationship directly? No. 2 to the one that's labeled in black up here is not, they don't have a relationship directly. So you see that I copied 1 down here, and now what is true about them? They're supplementary. Or I could have copied 2 up here next to the one that was given, and that's because of corresponding. And now I have a linear pair, which also adds up to 180. Okay, so be careful. This isn't me trying to trick you. You get figures that are drawn with angles in weird spots, and our brain wants to make them have a relationship, but we can't just force it. So this is a set equal to 180 type deal, and then work through. Let's see, we have a weird solution on this one. So it's the square root method, which is nice. I think that's easier, but it ends up with kind of an ugly answer. Does the negative root work in this case? Square root is 76. That would be a pretty small, relatively small negative number. So does it work in here? The only x we have to plug in is right there. What happens when you square something? Always, when you square something, what happens? Yeah, but what happens to the number? So somebody said it, I think. It's positive, right? If you square something, it's positive. Who cares what you plug in there? The result is positive. So don't both of these work this time? Are we getting that? That's kind of a big deal. That's like just a number sense thing. Do you understand what squaring does? That's not geometry, that's just number sense. So if you don't have a linear term, meaning there's no plain old x, then your negative answers will always work because they will become positive when you square them. Everybody good on that? Alright, how'd this go? This was a review of 2 things, the angle types, but also quadratic solving. So keep those thumbs, I'll look at you.
I have a question on
Okay.
one above.
Can you give me a thumb first? Okay. Alright, so she's going to ask on this one above. This thing is so annoying. Do you guys see how you can't see that scroll bar? We're supposed to try to find it on here. That one?
Yeah.
Okay.
So if you plug x equals 1 like into x for the 6x minus 7, it would
It's
be
also negative, yeah.
Yeah.
Do you see that? This is the 1 doesn't work too, also. What do you call that? If both your algebraic solutions don't actually work geometrically. What did you say?
It doesn't make sense.
Yeah, we said it was your abbreviation. What do you remember what it was?
No.
I think it was NSIC, no solution in context, I think is what he said. NSIC, he didn't want to write it out, but so yeah, good point. The 1 doesn't work either in this case. Alright, cool. Do you feel like you need more practice with solving these? Like, let me go find some. It's gonna take some scrolling. Just because we skipped over this, we're coming back to it today. So we did this one yesterday. There was no algebra, it was all just subtraction. But how about those kinds? That kind. Like, do you need more practice with that? Be honest. Okay. I don't have any printed, but I could maybe post some that's just practice identifying the angle types. I'm hoping that the algebra part is going fine. Is that true? Like, what kind of angles are those? What would you solve with? That's vertical, right? You don't even need the parallel lines, so just like the top one. I'll look at that. I guess I could maybe plug some of these slides in here. Like, is this what you're talking about? Like, just working through the angle relationships? Is that what you want more practice with?
That and trying to like finding the angles.
Yeah, I don't really know either. Alright. Think about it and then come tell me, and I'll see if I can find you something. Alright, guys, proofs. Proofs are a big deal. Big deal meaning, let's go all the way back to there. Proofs are a big deal because it teaches you how to form an argument. That's really the goal. If you have heard things about proofs, try to ignore that and make your own opinion about it. Some people talk to you and tell you they didn't like them or whatever. They're really not that bad. As long as you are good at logical reasoning, meaning I can start at A and make an argument to end up at D through several points, B, C, and D, right? That's all it is. Now, you have to know your geometry well in order to make those points. In other words, you can't just, like, mumble through it or whatever. Like, moving your mouth or writing with your pencil is not an argument. Does that make sense? I think, do you guys do this in your literacy classes where you have to construct some kind of a convincing proof of something? You ever done that? It has what's the name of it in ELA? What was it? CER? Oh, claim, evidence, and reasoning. Yeah, but yes, you're right. That is actually what it is. But isn't there a type of writing that you're trying to convince somebody of your point of view? What is that? Persuasive, yeah. Persuasive essay. Okay. That's us. That's what we're doing here. But you have to use geometry reasons. It can't just be, oh, it looks like or something. Okay? It's going to be geometric reasoning. But it's good. It teaches your brain how to think. And here's what I mean by reasoning. Reasoning means coming to a conclusion based on evidence or based on a flow of logical thinking. Okay? And there's two types that we do. Have you heard of deductive reasoning before? How about inductive? These are two ways, and there's another one, but we really only focus on these two. These are the main ways that we come to conclusions as people, not just in geometry, but in general. And they're kind of opposite of each other. So deductive, you start with a general idea, and then you think through how you're going to apply it to a specific context. Okay? So thinking like, driving fast without a seatbelt will probably get you killed. That's a general principle. Do you agree? So we apply that to the specific instance that I get in the car and buckle up before I drive to work. That's kind of deductive reasoning. Take a general principle and apply it to a specific situation. Can you think of one that you, and I'm not telling you to think hard, because everybody does this every single day. Can you think of one that you've done today, maybe? a version of applying a general principle to a specific case. What about my question earlier about what you do after school on a Friday afternoon? Do you see how that's like deductively reasoning, kind of like, hey, I know the general truth is I get out at 1:15 on Friday. I'm gonna apply that today to go do whatever. Make sense? Okay? And there's a whole bunch of other ones that we do. So general theory to a hypothesis, observation, confirmation of specifics. Okay, inductive reasoning goes the other way, but you do this pretty much every day as well. So you observe something specific, you notice a pattern, and then you start making hypotheses that you test and think about making a theory out of. We call that theory a conjecture. It's some kind of a generalized idea. So you've all done this before. Can you think of how? Does anybody have something from the cafeteria that you think is disgusting and you just don't eat?
Cookies.
Okay, that he used inductive reasoning to decide that. I ate one of the cookies. This is Julian. It was gross. Maybe it was an isolated event. I'll get another one. It's gross too. Now I see a pattern. Get another one. It's also gross. Now I have a hypothesis that the cookies from the cafeteria are gross. Right? And you kind of develop that into a conjecture that says, hey Tim, don't eat the cookies because they're gross. Right? And now our whole class thinks that. Okay? That's inductive reasoning. You said you had something too. What was yours?
Like I like chicken sandwiches, like the meat.
Okay. Chicken sandwiches are kind of good. I have an Italian exchange student in my calculus class that she is from Italy. She's going to be here all year, which is good. But I asked her what she had for lunch recently, and she had a burger, and she said, ugh. Like, compared to think about what she eats at home, right? She said her mom's a good cook in Italy. So, do you feel like you've done this before? Huh? Once or twice? Probably more than that. Okay. Here's an example. I have a student that when I walk past him in the hall, I can smell him. I have done that now 4, 5, 6 times. So my general conjecture is he needs to take a bath or wash his clothes or something. Okay? Like, it's just how our brain works, right? Anybody want to share one you've done? It's not you, Lyra. Anybody? It could be a good thing. Like, it doesn't always have to end in a bad thing. Do you ever go to Enstrom's for ice cream downtown? That's something our family likes to do, and almost every time without fail, it is a good experience. Like, they're nice, they're reasonably priced, it's good atmosphere, and so in our minds, we went once a long time ago, and we did it again and again, and we established this pattern that is a great place. Now we've influenced my family when they come to town. Their hypothesis and theory is, hey, it's a good place to get ice cream. It's a pleasant experience. So that's inductive reasoning. It's cool. Deductive, we already talked about. We will use both in here. Let's use it. See if you can try observing a specific case and coming to a conjecture, a potential theory about the rest of the situation. Okay? So 88, 82, 76. What is your conjecture for the next number in the sequence? 58, is that what I heard? Why? Do you know that it's going to be 58? But what is our brain trying to do? Yeah, like we see a pattern, and patterns, like our brains are extremely wired and created to see patterns. That's just how they work. So, but is it always true? Could the cafeteria make a good cookie?
No. Yes.
How about this one?
33.
I heard 33, and what was yours? 27. What, did you say 33? Oh. Do you need to sit in the front row?
No.
There's room. Do you? I don't think I've seen you with glasses. Alright, what's going on in that one? Well, it added 2, then added 4, then added 6, then added 8. So now it's going to add 10, so 33. Okay, so we're seeing patterns. That's inductive reasoning, okay? The thing that we're proposing as the next value in the sequence, so 58, 33, that's what we're calling a conjecture. It's that more than educated guess. It's based on a pattern that we think is accurate. Okay? Do you guys like visual patterns? So let's see if you can come up with the next dot pattern in the sequence. Okay, hold on. So we got him. Anybody else? Braden? Mackenzie, did you raise your hand? Is it because you can just see like this hazy yellow with black spots?
Yeah.
Alright. I'm not going to be able to fit it on here, but I could describe the thing. How's it going to look?
It's gonna have 5 terms and 28 numbers.
Well, the term count is just like counting which box, really. So this is the 5th version. So term in the sequence. And he said, what did you say, 28? What did you say?
30.
So do you notice the pattern is that we add a dot widthwise and we add a row heightwise? Does everybody see that? So this is going to have 6 dots. And it's going to be 5 high. 6, 4, 5. Okay. So how many is that? 30 dots. Okay. Again, could it be something completely different, like graph a flower or something, right? But I'm not trying to challenge your conjecture, just pointing out that it's not always correct. It's based on reasoning, and we do this as humans all the time. One of the many, many, many things that makes us not an animal. So a counterexample is something that disproves this conjecture. So in the things that we have said as our different conclusions or conjectures today, can you think of a counterexample for one of them? Let's go with Julian's. What would be a counterexample for his conjecture that the cookies from the cafeteria are gross? If what? But what's a counterexample? Not a counter theory or a counter conjecture, but actually a disproving counterexample. You're on the right track, but let's say it's slightly different.
Somebody eating a cookie and them thinking it was good?
Yes. That's exactly it. And it would be best if it was him, right? But yes, if we had agreement from the rest of you, hey, we just ate a cookie from the cafeteria, and yeah, it was good. That disproves, or at least challenges, the conjecture that it's not good, right? And so you can think of lots of those. Okay? Here's, is this cut off? I think it's okay. If an integer is, I think it's supposed to say odd. What is the problem here? Yeah, or cut off or something. I think it's supposed to say, you guys know what an integer is, right?
Yeah.
It's a positive or negative whole number. If an integer is odd and is between 1 and 20, then it must be prime. 10, and I'm going to add a 0 because the other thing had something missing. It doesn't totally matter. So give a counter example. If an integer is odd and is between 10 and 20, then it must be prime.
9.
You guys, between 10 and 20.
Oh.
16.
Well, I was just thinking 1.
Oh, okay.
16.
16 is not odd. Okay. 15, there we go. 15 is odd, but definitely not prime. Huh? If it was 1 to 20, then 9 would work, yeah. And also 15. So you just gave a counterexample. You picked out something that disproves the conjecture. Okay? Let's skip that. Okay. We've talked about this word converse, but I just want to tell you where it's coming from. So a conditional statement is an if-then statement. And so we have two parts. We have a hypothesis and a conclusion as part of that statement. The hypothesis is the if part, like you've heard the word hypothesis, you know it's not always true, right? That's the if it happens. And then the conclusion would be the then part. So if, then. It can be in a different order and still be okay. I have some weirdness going on with images here. Alright, Alberto can go to the movies if he washes the car. So which part of that is the hypothesis part? No. If he washes the car, that's the part that has to be done. And then the conclusion is go to the movies. So even though it didn't flow in the usual order, it's still connected in the same way. If he signs out, then he can go to the bathroom. That's a condition. Yeah, I just said that. I'm thinking proofs are going to go kind of rough right now. Alright. You can register to vote if you are at least 18. Where's the hypothesis in that? Where's the conclusion? Wait, it doesn't say then. Does it have to? Okay, here's another thing that you deal with pretty much every day. Even, like, not even related at all to geometry. Give me something like this that you maybe even were told this morning.
You can't go to Walmart if you left your car at home.
Yeah, that I could see that. I think that's like a converse version, or maybe what we call a contrapositive, but yeah. Say it again. If you say yours again.
Forget your card at home. You can't get it.
Okay. Yes, that works. If you forget your card, you can't go to Walmart. Any others from today? Did that happen to you today?
No,
That's good.
I lost it actually.
That's good. Nobody? You can go to the game tonight if you
Clean the dish. Oh.
clean the dishes. Have you done it yet?
No.
So you have that waiting for you when you get home?
Yeah.
Is it a lot? Good. Let's do that. Do you have a dishwasher? Alright. So here's the converse. We've talked about it. Do you guys remember what converse means? Do you ever read your notes after we write them down?
Not really.
It's obvious that it. Let's go. Read those notes. Converse means. Read it backwards. Remember that?
Oh yeah.
Now, you kind of have to adjust the wording a little bit. It's not like you can directly read it backwards, but that's the idea of it. So if you play a trumpet, then you play a brass instrument. First of all, is that true? This is a trumpet. Yes, it's a brass instrument. Okay, so going backwards, the converse, how would it sound? If
You might.
okay, then you play the trumpet.
What's the flip?
Wow.
So the original statement was 100% true. Is the converse true? No, because you could be playing a trombone, right? Or other versions. So this is not true. So sometimes when we flip something, it's not true. Now, think back to these theorems that we have written down. For example, one of the most recent ones was the alternate interior angles theorem. So it sounds like this. If two angles are alternate interior angles, then they are congruent. Let's flip that and say it backwards. If two angles are congruent, then they are alternate interior angles. That is not always true because we have now vertical angles are congruent, we have alternate exterior corresponding. So no, not necessarily. Okay, but we have had converse ones that are true. I'll have to think of it. It's slipping my mind right at the moment. So we use all of this kind of stuff to build a proof. You will do that. Kind of like this. If Alicia scores 85 or greater on her test, she will earn an A as her final grade. So let's think of it this way. If these two angles are congruent, then the triangle is congruent. If these two angles are congruent, then the lines are parallel. Do you hear a similarity in how we're thinking, these conditionals? Okay? What happens if she scores 89? What can you conclude?
She gets a B.
It's an A overall.
You must have hit your head yesterday in practice.
They're just some helmets.
Alright, we're going to skip these. Here's a proof. Go ahead and just on a scratch paper, the one I handed you is not this yet. On scratch paper, write it down.
Are we?
Hey, on scratch paper.
All you need to do, you don't need to write all the slide. You need this T, you need to write statements and reasons, and you need to write this algebraic equation, please. So proofs involve all of this stuff that we just talked through. Does anybody have any conjectures about proofs?
That's B's.
Okay.
Feels like constant.
Julian thinks that proofs are dumb.
I think we're just gonna have the two complexes next week.
Okay. Here's what I'm just going to work through these with you just to demonstrate. Number one, the statements. This is the development of the argument. You know, when I'm talking argument, I'm not talking about you bickering back and forth with your mom about why you didn't do your laundry. Like, that's not what I'm talking about. It could be if you actually use some logic, but what I'm talking about is like forensic arguing, court arguing, like when you're actually formulating a reasoned argument. Does that make sense?
Yeah.
Not just fighting. That's not what I mean. So the development of the argument happens on the left side. On the right side is the why. That's important. The why, or how do I word that? Or why you can. Let's say it that way. of each point. Okay, so I'm going to take off y. It's the y you can of each point. What allows you to do that? What allows you to draw that conclusion in a sequential manner?
Theorems.
So, you will start with the given. All your proofs will say what, and you'll be given something. In this case, you were given this equation. In our geometric proofs, you can already look at the sheet I handed you. Do you see how it says given on there? So you start by writing that. Like, you need to know what we take as fact. Sometimes it will be in a picture. It won't be written in words as much. But we start by saying, hey, I know this because it was given to me. Okay, now we're practicing on algebra because I know you know how to do these. What is your first step? Okay, so your next line is, again, your development of your argument. So it's 8x minus 6. So you write your next line in the argument. And why are you allowed to do that step? What mathematical property, principle, idea, or operation allows that?
Distribution.
Yes, the distributive property allowed us to do that. Okay, now what would you do?
Simplify.
What does our next line of our argument say?
X or 8x. Yeah,
Okay, so 8x minus 14. What allowed us to do that? And sometimes these are a little awkward because it's not like we name a property, but this is just subtraction. Or you could say combine like terms. Combine CLT, combine like terms. Okay, what would you do next? Next phase or next line in your argument.
Subtract the 2x and move it.
Okay? This illustrates that you don't always have to do a proof in a specific order. Someone else might have added the 14 first, and the proof will still work out. Okay, again, you're justifying. Sometimes this even says justification. So you're justifying why you were able to subtract 2x.
Because we're setting it to 0.
Not why, but why you are able. Why you can. That is, and so Kenzie said subtraction, but technically it's the subtraction property of equality. Because subtraction would say subtract 2x, right? But the fact that we did it on both sides is the subtraction property of equality. That's the mathematical reason for why we were able to do that. Okay? Now what would you do? Add 14 to both sides. And what do you suppose that reason is?
Addition of equality.
Yeah, addition, let's abbreviate prop of equal. Okay? Yes, we're going to abbreviate a lot because he wants to write all these words out. Alright? And then we know the last step is to divide. And that is the division property of equality. So now I'm really abbreviating, which is completely fine as long as it's completely clear what you mean. Okay? So division property of equality. That's totally fine. Okay, so you just did a proof. It's an algebraic proof. Okay, we will switch gears over to geometry. Here's what it would have said. Without all these words, in a very basic way, it would have said given the equation, and then it would have said prove x equals 3. Again, this stuff would not have been there. It just would say given that, prove that, you set this up, and you walk through your argument with justification. That's a proof. Right? If you can get good at this, it makes you a better, it makes you better at working with people in terms of interpersonal conflict because you think through it and you make logical arguments. Okay? Questions on that? Here's, by the way, just a quick list of these. We did addition, subtraction, multiplication we didn't do, but we did division. We did distributive property. We did combine like terms. But we're not going to focus on the algebra. We're going to have a whole bunch of these for geometry. So don't worry about looking at those. Do you feel like you need another algebra, or can we jump into those geometry ones? I'd rather do that if we can. Do you feel ready? I'm going to talk to this side of the room. I'm happy to do either one. You want to try another algebraic one? Alright. So I need to go find the geometry one. Oh, by the way, look. Given proof. That's how it's going to look. Is this one on your paper? Okay. I think it is. Yes, it is.
Yeah.
It's the first one, right? Okay. So this is a very typical geometry proof. Often it will have a diagram. Sometimes the diagram has stuff that's not mentioned, like information that's not mentioned in the text, but not usually. So we are given that angle 1 and angle 2 are vertical angles. We are told to prove that angle 1 is congruent to angle 2. So we are essentially, write this at the top, prove the vertical angles theorem. That's what we're doing. So we cannot use it to prove itself. Everybody follow that. If you want to convince your mom that you should be able to stay out later, you can't say, I need to stay out later because I need to stay out later. That doesn't work, right? You have to have reasoning in there. So what do we start with? What did I tell you in the algebraic proof? Always start with the given. So angle 1 and angle 2 are vertical angles. Again, abbreviate as much as possible where it still makes sense. So I'm not going to write angles, I'm going to use the symbol. What do we write for the reason that I wrote that? That's given. Okay? Alright, next line. Where do you think we're going to go to get to this point? Angle 1 is congruent to angle 2. This is where we start thinking about our argument. So someone walks in, they have no clue about this theorem. You have to prove somehow that those two are the same angle. Now, it's okay to use other geometry relationships, just not the vertical angles theorem. So any thoughts on how we could bypass that?
We can look at the image it shows.
Yeah, and when I look at that, I notice that angle 3 is there. Like, why would they put that there if I wasn't supposed to use it? Potentially, right?
You can use the linear relation, like 1 and 3 equals 180 and 3 and 2 also.
Okay, that's great. Did you guys hear that? These two equal 180 and those two equal 180. If they're adding to 180 with the same thing, don't they have to be equal?
Yeah.
That's what we're thinking right now. So here's how that goes. Measure of angle 1 plus measure of angle 3 equals 180. That's because of what we call, and you guys know the name, but we have to, when we're proving, stick the actual name of the idea at the end. So we know they're a linear pair, but the thing that says they're 180 degrees is the linear pair postulate. And you can abbreviate that LPP if you want. Okay, here's what we said. Measure of angle 2 plus measure of angle 3 equals 180. That's also true. And it's also because of the same reason, the linear pair postulate. Okay, so look what we've done. In our proof, remember this is on the left side, it's our reasoning as we work through our argument. We have said two different things plus 3 equals 180. Everybody agree? So our next line looks like 1 plus 3 equals 2 plus 3. Why did I take the left side of each and set them equal?
To show that they're all equal.
They're not all equal. We know that for a fact. Okay, do you see how they both equal 180? That means I can substitute one of these for the other one's 180. So we're doing just a mathematical substitution. We plugged in fact, let me erase this blue circle and I'll make that a little bit more clear. We essentially did this. We took this and stuck it in for 180 in the other equation because it equals 180 also. Okay? And now we don't have a 180 to deal with anymore. It's gone. It eliminated some information. Okay, now thinking back to the algebraic proof. We are trying to prove that those two are congruent. And we're pretty close. We just have this 3 floating around. What can we do to get rid of it? Subtract it, right? We don't have to show it. We're not doing the problem. We're just going to say that's true because we subtracted. And it's that subtraction property of equality. We just subtracted 3 off. Okay. Geometry, I think I've mentioned this, is OCD. Does this, the final green line, match that?
Yes.
No, it doesn't. This one says the measures are equal. That is algebra world. So algebra. This says angle is congruent. Do you see the difference? Measures are equal versus angles are congruent. So that's not the same. So we have to switch back into geometry land. Here's how. We just write angle 1 is congruent to angle 2. We know that's true. But why is it true? The definition of congruent angles is why. Again, abbreviate. So we switched back over to geometry to finish. Okay? And now that's the end of the proof. That's a geometry proof right there. What do you think? Yeah, like sometimes the OCD part is annoying because we knew here that they were equal, but we still had to take that final step to actually get back to what we were trying to prove, which was congruence. That's okay. Can I look at your paper real quick? Alright, so circle these to try for Tuesday. I want you to, oh, by the way, look on the back. Do you see how the left side is entirely filled out? We call those guided proofs where you're just plugging in information. So sometimes those are nice. I actually don't like them at all. So I want you to circle 2, 3, 4, and 6. Skip number 5. Do your best. You'll probably come back with a lot of these completely wrong, and that's okay. It's just giving it a shot. We are very, very early on in this.